Welcome back. In this lecture, we are going to talk about overset mesh. Overset mesh is a technique in which we can have two meshes which belong to different regions to overlap, and we solve in two different regions separately. At the boundaries of these regions, we interpolate values. We are solving consistently same problem in the entire domain. Let's see how this goes on. There are two blocks, and let me play this, and you can see that how the flow is forming. Here you can see a significant error or a change in resolution, but this is the result of the overset mesh. Since this is an example problem, I have not worked on that how we can resolve this particular problem. There you should have a similar or gradual resolution while you are working with overset mesh. We can ignore this for now. For these two blocks, I have used two different meshes that you can see here. If I go to the zone IDs, we can see the three zones with three different colors. If I go to cell type, then we can also see that wherever we have 0, in that part we are solving as usual. Wherever we have 1, on these cells we are interpolating. So we should have a background mesh from which we are interpolating. Clearly, using this particular technique, we can have meshes which are overlapping. These two are overset mesh, which are there for this particular object. This one is a square object, and this we have another square object, and these two square objects belong to two different meshes. Using this, we can also move these meshes independent of the background mesh, and we get very nice results when we have motion and we don't have to move the mesh. So the burden goes to the interpolation that is carried out here. If this much is clear, let's get started. Let's see how we can set up overset meshes in OpenFOAM. I have created a new folder, overset mesh, and here I have copied a simulation that we have done before, which is flow past a square. Here we have a mesh which remains constant in time. This does not move, as you can see here. We have some kind of vortex sharing that is going on. Now we want to change this particular simulation to an overset mesh simulation where we'll have a uniformly distributed domain with hex in the entire domain, and another mesh which is an overset mesh which will have this particular square in the middle, a smaller domain with little bit higher resolution. Let's see how we can change this particular simulation to the one which we just discussed. Let me clean the results so we can clean it by foam list times. One more thing that you should note that all the solvers which supports overset mesh start with overPimpleDyMFoam, similarly others. In this particular lecture, we are going to focus on overPimpleDyMFoam. Let me open VS Code. So first of all, what we want to do is we want to create two meshes, a outer mesh which is already here and another mesh which is inside this. Let's see how we can do that. We don't need these two. Let me delete these two. We don't need this pre-process and as well as this PDR block, and we are not going to decompose. Now we want to create another block for which we want x from negative 0.15 to say positive 0.15, and z equal to from negative 0.15 to positive 0.15. For this, these are the coordinates. If you don't know about this, whatever I'm writing here, it's written here automatically. It's due to one of the AI functions, one of the plugins which I'm using, which automates this writing. Just one thing to note here is that this is not an OpenFOAM syntax, and this does not come automatically in a usual editor. Now I can create the hex block here, which is something like this, and here I want little bit higher grading. Let me use this and 60, and this is also a smaller domain, So instead of patches, we'll use boundaries. Let me remove this and we'll use boundaries. Boundaries are same as patches, but here you can have different types. Instead of all as patches, we can have type wall and type overset. This is very important. Whatever is set as overset, there interpolation will take place. Make sure you select a correct side for overset, and then sides are the particular patches which are along the y-axis, and we don't want to do anything there. We'll set a slip boundary condition there. Then you can also have various other boundaries like bottom, top, which are wall, inlet and outlet, which are patches. If you are not sure that how you can set these particular faces, you can look at one of the lectures in turbulence modeling. There we have created two kinds of meshes. Now if this is done, let's create the block mesh. Here you can see we have two meshes. These are the two meshes which has been created, and now we have to create a small square in between this. For this we are going to use topoSet. If you don't know what a topoSet is, then you can view my previous lecture on the details about how to create a topoSet. I'll just add a topoSet dict. I'll just copy everything I have on topoSet. Just to give you a short overview of what topoSet dict do. topoSet dict helps you to select certain cells or patches or surfaces based upon whatever operation you are doing. This is variable declaration, and then you have actions. These actions, they always take place in this order only. If you have this above the previous one, then this one will take place first. Then you have to define certain parameters to it. For example, the name, you can choose any name. If this particular cell set exists, then it will load that and then do the particular operation. If it does not exist, then it will create a new one. Then there are various sources. You can have cell to cell, region to cell, box to cell, and various other. You can have some derived actions as well. This one is inversion. Similarly, you can have addition as well. It is selecting using region to cell, and after defining an inside point, you can create a cell set which is C0, which consists of the entire region 0. Then it is copying that region 0 to region 1 and then inverting it. So inverting it will give all the cells in region 1. Then it is copying everything in C1 to box, and then out of this box it is creating a subset which is the square box. The square box belong to that particular small region only, and then when we invert it, we'll get everything except this particular box. Three things that we required from this is this C0, which consists of all the cells in region 1, this C1, which consists of all the cells in region 2, and this particular inverted region which have the except the box, it has each and every cell. If we run topoSet, let me just make sure that we have the correct square side. If we run topoSet here and then use the subset command, this subset command works as this. This is the application name. It selects the box cell set, and then any patch which is newly created, it will name that as whole and then override the mesh. This has some problem with the pressure field 0p. Let's see what is that. It is saying that it cannot have patch field entry for a hole. We do not have hole here. That means we have to create some of the boundaries which were absent because we copied it from one of the previous files. Therefore we don't have all the boundary elements. Now here we have hole which is newly created. Hole here, this should be of type 0 gradient. We have overset. Overset is of type overset. Then sides, bottom, top, inlet, outlet, and cylinders. Sides, bottom, top, inlet, outlet, and there is no cylinder anymore. We can remove the cylinder. Similarly, we'll copy these two to velocity, and here you should note one thing, that you cannot have no slip boundary condition on the hole. You can only have moving wall velocity with velocity 0. Since our overset mesh can move as a whole, therefore it also requires interpolation. Moving wall velocity works very good with wherever we need interpolations. Therefore, we are making it uniformly 0 on the moving wall. This overset will remain overset here as well. We don't have a cylinder anymore. This is done. Now here you have these three, and this says overset. The error says that we need to have a value for the overset as well. Here we should have a value as well. So here we'll set uniformly 0, and for this one as well we'll set value uniformly what we have set here, which is the internal field 52. Now let's try to create, and after some warning you have all this created. And now if we look at the mesh, you can see that there is a square in the original patch. Now let's see what else do we need to change. One more thing that we require here is a zone ID. We can create a file as zone ID, and here for overset we have to have this overset as uniform value as 1. This will get overwritten by the set field, and except that we can have sides. Since it's a wall, we can have 0 gradient, and everything else will remain as is. These are the boundary condition, but we have to set the internal field according to the zone IDs. Therefore we have to use another application which is called setField. For that we need a setField dict. Let's use setField dict. Setfield dict is very easy. Since we have already created cell sets C0 and C1 belonging to different zones, we can just initialize a default value for the zone IDs, and then by using these cell to cell method we can select the cells and then set the field value as 0 for C0 and 1 for C1. Once we specify this, we can just run set fields and it will do it. It cannot find set fields dict because we have done a spelling mistake. So set fields dict, and now if we run set fields, and now if you look at zone IDs, you will see that it is populated with the values for 0 and 1 for 1. Now let's look at other things that we need to set. In the dynamic mesh you should have the overset mesh. Let's rename this to overset. This dynamic overset library is required. Along with this motion solver, we are not doing anything here with this particular motion, but still this is required. We cannot keep this empty. But if this motion is not doing anything, it won't change anything in the mesh. So therefore these are just dummy. Then in the control dict you have to have a library that you have to call, which is overset, and for FE motion solver you should have FE motion solvers. These are the two libraries which we are going to use, and then the overPimpleDyMFoam. We can keep all other values as same. We can just increase the time step by a small amount, and we don't need anything else for now. In the FE schemes we don't need to add anything else except one more additional detail about how the interpolation is going to take place when there are overset mesh involved. For this we are going to use cell volume weight method. There is inverse distance method and various other methods. Here you have to specify that what is the search box first. Our search box is this, which is the entire box, that principal diagonal entries, and then the division. Division helps search to happen faster. If you have 100 cross 60 divisions, then it will search within those boxes individually. This allow hole donors is required. Hole is the region where you don't want the calculation to take place because there is nothing going on. For example, in our mesh, the background mesh is available on the region where we have the square object. That particular location is assigned as whole. If there are whole donors involved, then whole locations can also donate the interpolation values. By default, this is always set to false. Then in the solution, make sure that you do not use a multi-grid solver. This is not suitable. And except that, there is no other things that you should do. I can remove all these from here. These are all standard solvers. This cell displacement is not required because we are not going to move anything. Let me just comment this because eventually we'll move this particular square as well. And with this, I think we can try to run. Now let's run overPimpleDyMFoam. This we have not saved. The control did. We do not have a semicolon here. We need point displacement because we have a motion involved. So therefore we have to add a point displacement. And let me just write some dummy values here. Everything is 0 and a uniform fixed value. And this we have to keep overset. Now we can try to run this. We have sides as empty. Here we'll keep the same as we have here. So we need cell displacement as well. Let me just check. Why do we need cell displacement? Since we are solving the mesh motion, so therefore it is looking for this cell displacement as well. Let's use this one only. We cannot use a multi-grid solver. Let me use a PCG solver. Now let's try to run PCG. So this particular solver we cannot use. Let me use another settings which works. I'm going to use this one and remove everything we had here. Let's try now. It seems to work. We'll wait for this for a while. So you can easily see that it is marking the patch cells and then doing the overset and the patch. So it has run for how much time? Let's see, for 0.135. So we'll wait for this simulation to end. Let's look at the results so far. We can see it is not correct. Let's look at the velocity. The velocity is getting restricted to just the middle portion, and let's try a split. See, in y direction. Here also we do not see much going on because these we have kept as slip walls. Instead of this, let's try making these sides as empty, which was there earlier. If this is empty, then everywhere it should be empty. Here it should be empty. Here also empty. For you, this is empty. And for zone ID as well, it says empty. Now we run this. Now we have some others also. There is some change. Let's wait for some time. So we have, so far we have results for 2 times. Let's look at those 2. Clearly the results are better. Let me just make it 2D. So you can see that we still have 2 meshes. It is solving the inner flow on the finer mesh, and then eventually it will go out of this. You can see that due to some resolution issue you have some problems here, but that requires practice. But you can see that the vertices are nicely forming and you have a better resolution for the vertex that is generating here as well. You can look at the zone IDs and you can clearly see the 2 zones, and you can also look at the cell types and figure out that which particular cell is getting the interpolation value, which ones are excluded from the solution, and which ones are the ones, the blue ones, where we are solving the entire equations. If this much is clear, then now we'll try to move this particular object. This one is easy. We'll just add a solver. Just go here and add a motion. We'll add a motion. Feel free to run the previously done simulation for a longer time to visualize more timestamps. In the dynamic mesh dict, we can add a solver, which is usual rigid body solver. This will move the moving zone that I think we have not assigned. Here, while creating, we have to assign. Let me also make this as empty, and we have to assign here this as moving zone. This one is a moving zone. Once we assign this as moving zone, whatever we decide for this particular zone, we can populate it here. You already know from one of the lectures. You can go back and see how we can do mesh motion in OpenFOAM. Now, if I start from the beginning, let me remove the mesh and then do the block mesh first. Then the next step was doing the topoSet and then subset mesh. Before doing the subset mesh, we have to remove everything that was here. Let me make this uniform again. Uniform 1, 2, 3, doesn't matter. Now I can run subset mesh. This has created a new subset mesh, and then I can run setFields. Now it is again populated, and now run overPimpleDyMFoam. This will now move the mesh as well. So if there is some motion, it will try to move that. We'll wait for some time so that we have at least 1 or 2 points on which we can visualize the results. Feel free to run for longer time as well. We have results for 2 times. Let's visualize that. You can see that this mesh was initially horizontal, this particular block. Now at 0.05 seconds it is here, and then in the next time step it is again rotated a little bit more. This particular motion is something that we have imposed, and you can see that you have some early vortices that are forming. You can see the LIC plot to roughly visualize that how it will look like. Clearly you can see that the Overset mesh is very helpful, where you can move and you don't have to move the mesh with that. You will just move the Overset mesh and have a desired motion for a particular object. Now we'll see that can we have 2 patches overlapping each other, as we have seen in the introduction, and still solve, so whether that is possible or not in OpenFOAM. First we'll create 2 blocks which are overlapping each other, and then we'll see that how we can modify it such that the Overset mesh works. In order to create 2 blocks, we'll first copy this, and then we'll make sure that our first point is at -0.15 as the previous block, but for the new block we'll move this till say 0.45. Similarly for the other one, and here we'll create these regions, region 1, region 2 and region 3. If you create these regions, these are helpful in order to select cells from these regions. The next region will be region 3, and here we'll just change it a little bit, let's say 280, and here in the Overset we'll have to add some faces, these 4 faces, and similarly for the sides we have to add these 2 faces, except that there is nothing else that is required. And now we'll again block mesh and we'll visualize what is created. I think I have to remove the previously created polymesh first and then run block mesh again, and now we can visualize. Let me just confirm that everything is fine. Yes. So let me first also remove all the results. After removing all the results, if we again run ParaView, then there is no error. That means those old results were creating the problems. And if we see this with edges, you can see that there are 3 domains, one up to this point, and the old domain and the background mesh. Now if you have seen the lecture on topoSet, then you may know that how we can remove squares shapes from both the region 2 and region 3. So let me do that. I'll just remove everything here and paste with the new one. Let me go through it, but this is straightforward. Our square side is this. Our x1 and x2 are like this. These are the points for the new square that we are going to create, and then we are creating cell set 0 from region 1. Similarly, from region 2 and region 3 we are using zone to cell source, and then we are creating a box, a copy of C1, and then creating a box out of it, then box 1 from C2, and then creating box 1 as a subset of box 1. Then we are adding box and box 1 using this operation, and then we are inverting the box. Except the box, we'll have everything. Let's see if that is going to happen. Running topoSet, then here in the zone IDs I have to remove everything. So uniform 0, and let me remove with this. Let me also copy this as .orig, which is the standard convention used in OpenFOAM. Now if I run, I have 3 regions now. So in the set fields I have to go and create one more, which is zone ID. For C2 I'll use zone ID 2. So now if I run, let me first create a subset box, which will, for all the new surfaces, it is going to create patch, and then we can run set fields. There is some problem with C2. In the polyform it cannot find C2. Let's see what happened here. In the topoSet, let me go to topoSet and see we have C0, C1 and C2 from region 3. It did not create it. Let's see what happened while creating this. It did not run at all after C0, then it created C1. We did not save this. Sorry about that. If I run it now, then I'll get C2 as well. Yes. Again, let me run blockMesh, then topoSet, then subset. Then again the inter field is populated. We'll move 0.orig to 0. If I run subset mesh, then it should work. So it worked fine. And then let us look at the mesh, the new mesh that has been created. And you can see that it has created 2 boxes. And now we can set fields, and let's check if everything is fine here as well. In zone ID, this is the zone ID, and it has not been populated. No, not this one, that one. Yeah, this is fine. In the 0 folder the zone ID is populated. Now we can run our overPimpleDyMFoam. There is some problem with the zones. There is no moving zone. Yes, we have to remove this. We don't want anything here now. We can set this to 0 and this to, say, region 1. Even though it is applying some motion to region 1, but it is not moving it. We don't want any kind of motion. And now it is running. We'll wait for some time to let it finish at least 1 or 2 steps. This did not run full. This was expected. What we'll do now is we'll change the write interval to something so that we'll know that what is going on. I'll run this. We'll have few time steps, and then we'll visualize that what is going on. Here you can see if you have any outputs. You have 2 files. Let's visualize them. Clearly this started. You can see that here you had something, but in terms of velocity there is a sudden jump. Let's make a threshold of zone IDs from 1.5 to 2.5. We'll get this zone, and then again go back to the original mesh and then make a threshold of 0.5 to 1.5 for the zone IDs. Then we'll have this one, and the last one is the original zone, which is from negative 0.5 to 0.5. This is the original one. So if we go to the velocity, so velocity ranges from 0 to 4. for this one, the range of the velocity is again 0 to 4 for this one as well. Let's look at this one. The range of velocity is again 0 to 4 for this one as well. But for this one, the velocity is around 2, which is our inlet velocity. Clearly, there is a jump. If we just look at the cell types here, let me just switch off this domain and just look at the cell types. Here also, just look at the cell types as a block. Here you can see that the interpolation is going to take place on these cells. But if I switch this off, we will see that interpolation is also going to take place for the other region on the same cells. Right now what is going on is interpolation is going to only one of the cells, not both the cells. Therefore, while using overset mesh, you should make sure that two of the overset meshes never overlap. The interpolation points, they should never overlap. The part of the domain can overlap. We'll see that how we can simulate this, how we can change the size of the domain and simulate this particular problem. I'll just undo this so that we have our original right intervals, and then go to blockMesh ticked. Here we can change the size. I have already created these. Let me use those sizes. This is the one. A little bit fancy here, but doing the same thing. Instead of writing 0.15 again and again, I wrote sides again and again, but I can easily change just one value and get different size for the domain. That's why this is more convenient. Then this is another domain which is just different points. We'll see that what are those different points. We'll run blockMesh again. Let me clean everything first and then run blockMesh. Let's look at these domains. So you can see that these are the two domains, and it does not have a square patch in the middle. That will be created using the topoSet and then subset mesh. Before that, we have to copy everything from 0.orig to 0 and then create a subset mesh from the box, and then we have to set field, and let's visualize the initial mesh. So you can see the two boxes are in the same place, but the outer domain for the other one is not overlapping. They will just overlap for one cell over here, except that there is no overlap. Let's see whether this works for this or not. Of course this will work because this is the simulation that I showed in the introduction. We have results from 2 times now, so we can cancel this and look at the results. Here, let me make this 2D. We can see that there is no velocity jump and the vortices are evolving as expected. And here you can again see the cell types, and you can visualize that which cells are interpolating. There is this little bit overlap, so there we have some errors. Except this, there won't be any error because the interpolation points are different for different domains. So this is how you can have overlapping overset meshes, but this is not the best way to use overset mesh. You should always make sure that overset meshes are completely detached. They rarely overlap, and then you can expect some accuracy. But you can actually code and handle these special cases and then work with your particular setup. If you go to the OpenFOAM website or any of the forums which discusses OpenFOAM, you can see that many of them will say that OpenFOAM does not work well with overlapping overset zones, and that is correct. You have to handle these special cases. For example, here there will be some errors, and this particularly small overlap will result in larger error over time. You should not rely on these kind of results when there is an overlap. By default, it won't work. Make sure you understand this. With this, we can stop this particular lecture. If you have liked the content of our channel, then please like, share and subscribe to our channel. Thank you.